The thrust of my presentation here is to talk about how paying close attention to the biology of the process can really optimize the economic and environmental outcomes of composting. As you can tell from reading the synopsis, I feel like a lot of our industry has run towards very expensive engineering intense solutions to try and control odors, and with very mixed success, I may add. On the other hand, it's much less expensive almost always to take really good care of the biology, and it comes with all kinds of other benefits. So I'm going to go into some detail on all of this. It's what I call a root cause approach. So there's a lot of topics to cover here. I just taught a class this morning, in fact, went on for an hour on similar topics, and I felt like I only touched some of these topics briefly. So in 30 minutes, I think I'll probably raise more questions than I answer, but that's okay. I'm hoping that it starts the conversation, starts the scientific inquiry, and helps drive the whole process ahead towards a more sustainable and cost-effective industry. So I necessarily have to focus in on a couple aspects of composting. I don't have time to talk about all different types. So I'm going to talk about aerated compost, that is forced aeration with blowers. And I'm going to talk about two feedstock groups. The first and the primary one, I'm going to talk about what I consider feedstocks that are acidic and energetic. And these are curbside organics, food waste, green waste. The second group is feedstocks that are high in nitrogen and tend to be pH neutral and alkaline, like biosolids, digestate, animal byproducts. I won't spend a lot of time on those. A lot of the ideas I present with the acidic and energetic feedstocks do apply, although the one big caveat is it takes a lot longer to stabilize high protein, high nitrogen feedstocks than it does these more carbon-rich feedstocks. In terms of odor sources, of course, there's many at a compost facility. Again, I'm going to focus on the ones that have to do with active composting, maturation, and then occur in storage and loadout. I'm not going to talk about housekeeping and design elements of raw feedstocks and leachate, odor management, although those are very important. I think those are more straightforward kind of engineering and housekeeping, and I'm going to focus on the process-oriented side of odor sources. So fundamentally, there's something that I call the odor equation. It starts with odor generation, odor units per ton per minute. And you multiply that by the quantity, the tons, that's your total odor flux. And then you reduce that by the percent capture, 1 minus that percent capture. And then you reduce that again by how effective your control methodology is. Typically, it's biofiltration. And what's left out of that is going to fugitive odor flux. So capture is enclosing in some way or another. It's either putting a building around it or sucking air down through. Control, of course, is scrubbing. But the root cause of all these odors start in odor generation. And what we find is that capture and control can both typically reduce odors on the order of 90% each, but root cause can, the difference between a facility that's well run and poorly run can be a factor of 50 difference in odor generation in terms of OU per ton per minute. So I maintain we should focus there first and then only add enclosing and scrubbing if it becomes necessary. So a lot of money's been spent on enclosing facilities. These are all, the one on the top left is near Halifax. The one on the right, top right, is Wilmington, Delaware. Lower left is London, Ontario. Lower right is Hamilton, Ontario. All of these quotes in here I just took right out of the local newspapers that were online that published about them. And these are their photos as well. So these were rather expensive, but they didn't somehow control odors. This is one you're all much more familiar with than I am, and hopefully I don't misspeak here, but I did read this, the processing plant odor reduction options assessment. It was interesting. I've also read other details on this facility in Christchurch. And apparently the bulk of the odors came from the windrows outside of the plant. That, of course, tells us that they were not very well stabilized. Otherwise, they wouldn't be capable of generating odors. So in that assessment, they went through a series of options of how to address the problem. And I can say that I couldn't see in those options something that would have made me want to invest in them. And then when I did a word search on the assessment, found the word oxygen 6 times, but never with any sort of number attached to it. And then all the other key process indicators, pH, density, moisture, carbon, respiration, 0 mentions of any of those. And in the text, they talked about the tunnels running at 60 to 70 C without any understanding of how that might affect the stabilization coming out the back end. They made a comment about recirculated air having lower oxygen content. It's not really the case. You use a very small amount of the oxygen in air when you're aerating something at any kind of normal or rate, a few percent maybe. So that was a little misconception. And then something about, and once the material came out to windrows for maturation, that they're turning them to increase the oxygen at the center of the windrow. Well, the oxygen at the center of the windrow typically gets used up in, for the most part, in about 15 to 25 minutes, depending on how active the windrow is. So it's not really an effective way to change the oxygen level at the center. And then there's the assumption that no odors were being exhausted through the biofilter. If you think back to the odor equation, we know that's not true. We also know it because I personally have done quite a few odor studies on biofilters. There is odor from biofilters. So, and I don't mean to be critical here. I'm just saying that generally speaking, compost process science isn't broadly understood, isn't broadly practiced, and people are asked to do work for which they haven't had the opportunity to be trained. And so our industry needs to kind of mature in that way. And certainly the same is true here in the US, same is true in Canada. So some more of the downsides in closing a facility. First is it's a high corrosion environment. I'm familiar with 2 facilities that have things drop out of the ceiling and injure workers because they corroded and fell. Another facility that was closed 5 years before it was supposed to. And that facility was completely lined with stainless steel. It takes a lot of fan power to ventilate a big space, and you have to ventilate a big space if you have front-end loaders and people and so forth in there. You need really big biofilters when you have really big ventilation systems. Those are expense to maintain, to build. And if any of you has ever been inside of one of these facilities on a cool day, you may have noticed how bad the visibility can be. And you can't really overcome that with ventilation. It's just really not possible. So can we afford this? Well, I was just in Montreal and saw the Saint Laurent facility, which is mostly done, but in litigation over cost overruns. This is just one snapshot. Unbelievable complexity. I just was slack-jawed the whole time walking through there. I don't know that this is sustainable. Here's some numbers to kind of fill you in a little bit. The Edmonton, Alberta facility that was built in '98 was about 1,500 New Zealand dollars per metric ton of throughput. The Hamilton, Ontario one that was closed down was a little over 900. The one in Calgary, Alberta, which is more recent, it's also roughly $1,500 per wet ton of throughput. And this one, Montreal Saint Laurent, takes the cake at $3,600 per ton per year of throughput. And it's going to go up. It's going to cost more than that by the time they settle the litigation. I think there's more cost-effective ways to save the planet. And if we're willing to spend this kind of money, maybe we should look at more electrical vehicles and better insulated homes and things. But in any case, there are people out there spending excessive sums. So if we turn to compost science and ask the question, how do we minimize odors? There's a simple answer: just avoid all the common process inhibitors. That's the simple answer. How we do it is a little more complicated. But it really comes down to 3 key things. First of all, do not start with a poor quality mix. I think you all understand best management practices, how to make a good mix, seed and density, moisture, all these standard things. Number two, make sure your process never experiences low oxygen availability. And I'll explain what that means in a moment. Number three, make sure that if you have a low pH feedstock like food waste and green waste or curbside, make sure that you get through that low pH and avoid high temperatures early until you have. So here is a graph. We have a process lab here, and we can run about, these are 15-liter vessels, and we fill them with a mix. And these are all the same food waste, green waste mix, all three of these. And then the mix was good. The oxygen availability was good, but we ran one with high pH inhibition, one with semi-inhibited, and one without. And on the left-hand side of this graph is the CO2 evolution during the first 8 days. And you'll notice that in the uninhibited case, we made way more progress, because really all that composting comes down to is the production of CO2 leading towards a stabilized product. We're trying to bio-oxidize the very putrescible part of the feedstock. And so the faster you get that done, the faster you get to stability, which is good for end-of-line odors. But it also, as it turns out, it produces much less odorous carbon compounds if you're thoroughly oxidizing the organic matter all the way to CO2. So that top line was fast composting, low odor emissions. The bottom line, hardly any progress being made, and high odor emissions. Mixed parameters, again, you probably all know these things. When it comes to concerns around odors, we don't really worry too much about both minimum and maximum in most areas. It's just we want to be either under or over. So for instance, well, moisture content, we have a range we want to be in so we don't run out of moisture. But carbon to nitrogen, we just want to be above, say, 23. 25 is ideal, but at least above 23. Density, we want to be under 560. And settled pile depths in meters, about 2.75. And then there's also particle size distribution. These are just kind of guidelines. We want almost a third really small particles, a third medium, and kind of a third less than 10 centimeters. Then in addition to that, you need to make a homogeneous mix. And stationary mixer is just one way to do it. You can do it a couple other ways. You can't do it very well with a bucket. You can do pretty well with a wheel loader that you do coarse mix and drop through a grinder. But in one way or another, you want to hit these parameters more or less, and what we call a best management practices mix. So remember back, I used the phrase oxygen availability. It is key to minimizing odors. And where's that oxygen have to be available? It has to be available, it has to be dissolved into that liquid film that surrounds each particle. And that amount of oxygen that's found in that liquid film is controlled by both the temperature of that environment and the percent oxygen that you find in the pore space. And Nick Sauer from UK Environment has done a great study on this, and you can find it online and you can find it at our website. But really what he pointed out is your minimum design goal should be continuous oxygen levels in that film layer above 3 parts per million. Now this colorful graph in front of you, all the little numbers in the colored portion of the graph are parts per million oxygen dissolved into that water layer. On the left is the pore space oxygen, across the top are temperatures. So you want to be above that red line. And you notice that red line has a big slant to it. It's a big gradient to the left. So as temperatures go up, to stay above 3 parts per million, you need higher and higher oxygen levels in the pore space. So a high aeration system should run up around in that green box near the top, kind of between 45 C, 70 C, and should have 3 to 5, 5.5 parts per million. A low aeration system is going to be down in that yellow zone, well below the 3 part per million line. That's down between 1 and 2 parts per million. And if you're looking at what happens when you have a fan that goes off and on in an active system, if it's been off for, say, 15 minutes, usually you'll be below 1 part per million. So that's creating lots of odors. And you want to hold it in that condition until you achieve a Solvita over 5. And I imagine you're familiar with Solvita index. You can also measure it in CO2 respiration or standard oxygen uptake. There's tables where you can look up how those all connect. The next big process variable that controls both the production of odors and inhibits the stabilization of compost is the pH. This is based on the work of Dr. Celia Sundberg. And at the end, I provide a bunch of references for these folks. But what she found out, she was working on her PhD in Sweden when they were having all kinds of odor issues in the Swedish compost facilities back in around 2003, 2005. And they had started collecting a lot more food waste and adding it to the green waste in these compost facilities. And the facilities that have been doing pretty well before are now having lots of odors. So she started a study to figure this out. And what she found out was you have, and we know this from practice, that there's basically 2 kinds of bacteria that are working in a compost pile, aerobic bacteria, mesophilic and thermophilic. The mesophilic bacteria are functional below 45 centigrade, and the thermophilic are functional above that. Turns out the mesophiles can handle low pH materials because they can neutralize the organic acids. If you let them, I'm going the wrong way here. Okay, let me back up one moment. Curbside comes in usually at pH between 4 and 5. But if you let those mesophiles do what they can do, they'll raise the pH up above 6.5, which she found to be kind of the magic line. And then you can let that whole process heat up into the thermophilic zone. You get very efficient composting. On the other hand, if you go straight from raw feedstock up over 45 and you don't give enough time for that mesophilic transformation of the organic acids, you hand the thermophiles acidic feedstocks, and the thermophiles are strongly inhibited by acidic feedstocks. We've tested this repeatedly in the field. We found it true, and she has some great data here that really shows it. The top is the slow heating method, where you have 2 days, 48 hours at approximately 40 degrees centigrade, initial pH of 4.5, and at the bottom is fast heating. So you had day 1 around 40, but by day 2 you're up to 55 centigrade. And remember, at 55 centigrade, the mesophiles can't neutralize the acidic components, and that you're handing that on to the thermophiles. So what we see here on the left-hand side is CO2 evolution per day. And in the slow heating or the mesophilic period, what we see is a big spike of CO2 production. And CO2 production is the fundamental metric for progress in composting. Down at the bottom, you get a little spike of CO2, then it goes almost to 0. On the right-hand graphs, those are VOCs, volatile organic carbon, or compounds, excuse me, concentrations on the left and odor on the right. The material then went through the mesophilic period. You get a little spike of VOCs, which is probably VOCs that came in inherent in the feedstocks at the beginning, and then gets ventilated out, and then you don't produce more after that. The odor are shown as dots, and that's a log scale on the right. You compare that to the bottom, you can see not only are there far more VOCs produced on the bottom, there's also much higher odor, about 50 times higher on the odor concentrations. It's just indicative of what happens when you have inhibited composting. So she found that with 48 hours of cooling, adequate cooling, you can see what the pH does in these various batches, and it has no impact on what the oxygen is. She has 1%, 16% oxygen. Didn't impact how the pH changed. It's just temperature driven. And it also didn't what happened after day 2 in terms of the temperatures. In one case, they went up to 70. In another case, she held them at 55. Also didn't impact the pH shift. Only the initial 2 days of temperature. And in terms of difference of odor units that she measured at both large scale and bench scale facilities, factor of 50 difference between the materials that got stuck at a pH of 5 and the ones that went up to 7, 8, 8.5. So how do we avoid that kind of process inhibition? Well, you need enough airflow to maintain the pile temperatures below 45 C for the first 2 to 3 days. If your feedstocks are just mildly acidic, what we found through testing, if you're say 5.5 to 6, you probably can get it done in 1 day. But if you're down around 5, 4.5, you're going to need 2. And if it's closer to 4, you're going to need 3. It's a concentration reduction process. And then the other thing to keep in mind is keep the oxygen levels in the film layer above 3 parts per million until you have adequate stability. The graph you see is one of heat generation. This is what you'd expect. Early on, you generate more heat than you do later. So you need most of that high cooling effect or the high airflow early. Sometimes it might seem like excessive airflow, but one of the ways to achieve that is to have a zone where you put material in a very relatively low depth pile, aerate it for a few days, and flip it into a more normal pile, if your material is acidic enough that you need that. And what kind of aeration rates are we talking about? Well, in meters of air per hour per cubic meter volume. First 3 days, you might need something 8 to 20. That's pretty high. Day 4 to 14, more like 3 to 8, and thereafter 1 to 3. So that first day is really to get through that mesophilic period. Then after that, it's just to keep up with oxygen demand and to not allow the temperatures to run away. We don't want to see temperatures up at 80 C, 75 C. We want to keep them below 70. That avoids thermal inhibition. So some of the advantage of this approach, obviously lower odor generation during composting, less need to capture and scrub your exhaust air, and shorter retention times. You're making a lot of CO2 quickly. You're getting your process material in, getting material out. And then the other big advantage is you have more stable material going to maturation and stockpiles. You don't have stinky windrows outside of your facility that are causing odor every time they're turned. They're lower odor potential. It requires less management and shorter retention times as well. I'm not saying that odor capture and control is never required. It is sometimes. Certainly, it should be considered if you're taking very odorous feedstocks before you have them mixed with an amendment that can absorb their odor, like a ground wood. It can be a wise and worthwhile thing. But the other place that we find is that in the first 1 to 4 or 5 days, especially day 1 through 3, as materials are heating up, we tend to volatilize the odorants that come in with the feedstocks. And so you need to manage those. And you can do that with negative aeration and just suck it down through the pile and blow it out to a biofilter, or you can cover it if you need to. But depending on the sensitivity of your site, you might need to do that for the first couple of days. Now, remember that the fears that we have about odors are really generated by facilities that have generated odors over the whole retention time. They've never got through the pH transition, so they're used to really high odor fluxes the entire time. So if you have a facility that only has a higher odor flux a small portion of the time, then with relatively simple means, you can probably control that enough to be a good neighbor. And one thing you should know, that VOCs are proportional to odor units. This graph on the right, data from Dr. Tom Jobson at Washington State. He's in the midst of a kind of year 2 of a 4-year project to measure compost air emissions from compost piles based on different process conditions, and we were lucky enough to provide him a system to allow him to do that. So if you're going to do some sort of odor capture and control you need to do it without inhibiting the airflow. So a biolayer on top of the pile, which we'll talk about, doesn't inhibit, but most of the fabrics that you can put on top of a pile do. We tested a bunch of fabrics in our lab, looking at what the pressure gradient was across them. We found out one thing that was interesting, and makes sense, is that a wet fabric has a much higher pressure gradient than a dry fabric, and that's because the drops are actually plugging all the little micropores. But in general, you can't really generate enough air through a pile to cool it if you have a fabric layer on top. You really need a very low pressure so that on that cover layer, whatever it is, so you don't generate excessive force. And we believe that's below 50 pascals, which is quite a low pressure. So here's basically the biolayer I talked about. It's pretty simple, goes on top of a positive pile, and when you irrigate it, it wets the top surface and cools it. And if you think back to that chart of Henry's law that Nick Sauer developed, it shows how you can dissolve more gases as in the film layer as the surface is cooled. The same is true for a biolayer or a biofilter. That's why you need moisture in those layers for them to work most effectively. You don't have to irrigate all the time. Just we find typically, this is in California where it's hot and dry. They usually run their sprinklers for 5 minutes every 2 hours on a hot day and 5 minutes every 4 hours on an average day, and not at all in the winter. Fixed biofilters are another way to achieve this. This is a more expensive way. All these aeration parts need to be stainless steel to handle this corrosive material. It does work relatively well. So the negative aeration portion of one of these systems pulls the air down through the pile, pushes it up through the biofilter. Again, you want irrigated biofilter media to make sure you have good efficiency. This facility actually is near in the Los Angeles area where they have very extreme VOC emission regulations. And you'll notice that on top of all those piles, there's also surface irrigation. When we measure air emissions off the surface of a negatively aerated pile, we're usually measuring rates that are very near background. In other words, we don't really get anything up through the pile, but the consent decree required it, so of course we did it. Here's a facility we're pretty proud of. This happens to be in Lethbridge, Alberta, Canada. It's open air. It's reversing aeration in those bunkers in the active CASP, which CASP stands for biolayer covered aerated static pile. And that's where the primary composting goes on. And then the maturation is a positively aerated CAFS on your left. And one of the reasons we're proud of this is because Canada is the land of enclosed composting. And in Alberta, they've had a lot of big, expensive facilities. This facility doesn't seem to have odor problems. They make a real nice mix. They keep oxygen availability high. They aerate it enough initially to get over the pH hump, and it works rather well. So that's just how the material, they are tipping and mixing and grinding inside of a building. They bring it out and just with a bucket loader, throw it in the pile and then biolayer cover it as they go. And from the cast, of course, it goes to maturation. They're just a short list of design and operational guidelines. Of course, start out with a BMP raw mix. If one parameter is out of range, and in composting, you know, this is not precision work really. We're not making pharmaceuticals. You just need to be in the right ballpark. But if one's out of range, the others should be further in range. Don't be out of range with 2 parameters. You really should assess the biodegradability of your feedstocks. If you have a lot of food waste, you know you're going to need more air. If you have a lot of wood, you can use less air. If you're in the maturation phase, less air. So adjust your aeration system accordingly. You want to assess the stabilization rate of the process and the size the retention time accordingly so that you are sure to achieve a Solvita better than 5 or a CO2 respiration below 7 during that active phase. So that might take some testing. You can, if you have a process lab, you can do it, or you can do it. Most people just have to build a small pilot to figure that out. In odor critical applications, you got to consider enclosing, tipping, and mixing, and to provide the appropriate level of capture and control during the first few days of the active composting phase. Here's a whole bunch of references, my email, because I figure you'll have questions. So to the extent that you're interested in this level of compost science, here you go.